At 6 o'clock on March 27, 1945, Squadron Engineering Officer Daryl W. Landau stood beside a smoking Wright Aeronautical at North Field, Guam, watching mechanics wrestle the charred remains of cylinder number 14 from the rear row. He was 31 years old, 6 months into his tour with the 19th Bombardment Group, and in the past week alone his crews had replaced 18 burned-out cylinders. The Japanese had shot down 14 B-29s over Tokyo in a month. Engine fires had destroyed 23 more. Since February, Landau had watched 5 Superfortresses erupt into magnesium flame on this very runway. Crankcases igniting at 5,600 degrees Fahrenheit. Wing spars burning through before pilots could clear the tree line. Crews dying in aircraft that never reached rotation speed. The pattern never changed. Rear cylinders overheating during takeoff, exhaust valves failing, fire spreading faster than the extinguishers could flood the nacelle. By the time a pilot feathered the prop, the wing was already lost. Wright Aeronautical had issued 48,000 engineering changes to tame the duplex cyclone. New baffles, revised exhaust collectors, tighter cowling clearances, different carburetor elbows. Engines that once averaged 100 hours between overhauls now survived 400. 400 hours still meant catastrophe for an airplane expected to fly 3,000 miles to Tokyo and back. Guam's tropical heat made everything worse. By mid-morning, the runway temperature hit 125 degrees. Pilots taxied fast, trying to keep air moving through the cowlings. Flight engineers watched cylinder head temperatures climb past the red line on every takeoff roll. There was no safety margin. Every mission began with engines already flirting with failure. Wright Field's solution was fuel injection. Rip out the carburetors, retrofit the Pacific Fleet. Months of work, millions of dollars. Bombers pulled from combat during the decisive phase of the war. Fuel injection might solve mixture imbalance. It did not explain why certain cylinders burned while others survived. It did not explain why cylinder number 1, positioned directly behind the largest obstruction at the engine's nose, almost never failed. The cylinders that died were always elsewhere, always counterclockwise from the front view. As the mechanics lowered the ruined cylinder onto a stand, Landau looked up at the engine's face. The massive propeller governor and twin distributors mounted like football-sized barricades in the intake stream. The R-3350 displaced 3,350 cubic inches across 18 cylinders arranged in 2 rows, generating 2,200 horsepower. All of it depended on air flowing through a cowling design before anyone understood what maximum gross tropical takeoffs would demand. That air had to curve around obstructions, had to swirl through baffling mint to distribute it evenly. And it was swirling counterclockwise on every engine, every start, every takeoff, missing the very cylinders that kept failing. He stared at cylinder number 1, the cylinder Wright had designated as the worst-case indicator, fitted with the thermocouple that was supposed to warn of impending disaster. It should have overheated first. It almost never did. It sat in a dead zone behind the propeller governor where the vortex never reached. The so-called indicator cylinder was the coolest on the engine. The ones starving for air were positioned where the swirl stripped cooling flow away. The answer was suddenly complete in his mind, and he had no idea whether anyone would listen. Landau had arrived with the group in January, expecting paperwork and inspection reports. Instead, he watched B-29s burn. On February 16th, a superfortress named City of Angels, loaded with 10,000 pounds of incendiaries for Tokyo, advanced throttles for takeoff. Temperatures rose as expected, then cylinder 17 on the number 3 engine failed. An exhaust valve broke loose. Combustion gases ignited the magnesium crankcase. The pilot chopped power and triggered the extinguisher system. Too late. The wing spar burned through before the aircraft reached flying speed. The bomber disintegrated at 130 knots. All 11 crewmen died. The crash board cited worn valve guides and recommended tighter inspection schedules, the same recommendations issued after every previous fire. They addressed symptoms, never causes. Landau stopped reading reports and started watching engines. He stood on the hardstand during startup, observed propellers turning through compression, ignition sequences snapping alive, cowl flaps adjusting as temperatures climbed. He watched exhaust gases curl. He watched cooling air enter the nacelle and vanish into baffling design to channel it evenly across both rows. The baffling assumed smooth airflow, unobstructed entry, no turbulence. No one had tested that assumption at maximum weight, in tropical heat, with propeller governors and distributors sitting squarely in the primary flow path. He pulled cylinder replacement logs and charted failures by position. Cylinder 1, 3 replacements since February. Cylinder 4, 11. Cylinder 7, 14. Cylinder 10, 9. Cylinder 13, 16. The counterclockwise arc of destruction was unmistakable. He presented the data to the group maintenance officer and outlined the airflow theory. The response was curt: keep aircraft mission ready. Engine design belonged to Wright Aeronautical. Squadron engineers repaired airplanes. They did not redesign them. So Landau went back to the line. On March 21st, he watched a morning engine start and saw it clearly. The propeller's rotation creating a counterclockwise vortex over the nose case, deflecting primary cooling air away from specific cylinders. Those cylinders relied on secondary flow that disappeared when cowl flaps were set for takeoff. They were starving, cooking, failing. Cylinder 1 remained cool precisely because it sat in stagnant air behind the governor. Wright Field had spent 2 years trying to force more air into the cowling. Landau realized they were forcing it into the wrong places. The R-3350 duplex Cyclone was the most powerful radial engine in combat service. 18 cylinders, twin rows, dual superchargers, each cylinder displacing 186 cubic inches, enough thrust to lift 65 tons of bomber and fuel off a coral strip and climb toward 30,000 feet. It was also a metallurgical gamble: magnesium alloy crankcase to save weight, a single forged crankshaft driving both rows, exhaust collectors gathering flame from 9 cylinders at once, baffles machined to thousandths of an inch. Any single failure could destroy the engine in seconds. Landau understood radial engine theory. Air-cooled cylinders depended on uninterrupted flow across their cooling fins. The fins increased surface area, transferred combustion heat into passing air, and carried thermal energy away faster than the engine could generate it. If the air never reached a cylinder, the mathematics collapsed. Metal exceeded design limits. Valves failed. Magnesium burned. Crews died. And standing on that hot Guam runway, staring at a blackened cylinder and a governor blocking the intake stream, Landau knew the engine wasn't dying from weakness. It was dying from misdirected air, and that meant it could be saved. Simple physics worked beautifully when the aircraft was moving. It became catastrophic when it was not. On the ground, at 5 knots of taxi speed, the R-3350 received almost no effective cooling. Pilots minimized ground time. Flight engineers watched cylinder head temperatures with obsessive focus, rushing magneto checks and advancing throttles the instant they reached run-up position. Even then, temperatures climbed toward red line before the aircraft ever began rolling. But some cylinders reached red line faster than others. And they were always the same ones. Counterclockwise from the front view. Exactly the positions Landau had marked in his failure logs. The propeller governor sat at the 12 o'clock position, a massive mechanical housing converting engine RPM into thrust, essential for variable pitch control and perfectly positioned to block airflow. Twin distributors flanked it at 11 and 1 o'clock, equally large, equally obstructive. Together they created stagnant pockets where cooling air never properly circulated. Cylinder number 1 sat directly behind the governor. It carried the thermocouple sensor. It transmitted temperature data to the flight engineers panel. Wright Aeronautical had designated it the worst-case indicator because they assumed it would run hottest. They were wrong. It ran coolest. The counterclockwise vortex of cooling air never touched it. It sat in still air, receiving minimal cooling, but also spared from the heated exhaust wash sweeping across the cylinders to its left. The cylinders that actually failed were positioned where the vortex dragged hot exhaust gases across their fins, compounding thermal load. They ran lean. They ran hot. Exhaust valves warped and burned. Guides failed. Magnesium ignited. And Wright Field never saw it, because their temperature sensor was mounted on the safest cylinder on the engine. Landau sketched everything on graph paper. Front view of the engine. Governor at 12. Distributors at 11 and 1. Cowling inlet. Baffle layout. Observed counterclockwise swirl. Then he overlaid the failure data. The match was perfect. The solution was not exotic. It did not require a billion-dollar retrofit. It required oil. Specifically, direct oil flow to the exhaust valve rocker arms. Cool the valves internally. Bypass the flawed external airflow path entirely. Drill the mounting bolts. Replace the solid rocker support bolts with hollow ones. Route pressurized oil through them. Deliver cooling exactly where the failure occurred. 6 hollow bolts per engine. Minimal machining. No structural redesign. No fuel system overhaul. It was elegant, and Wright would never approve it. The fuel injection conversion was already funded, already in development, already promised as the answer. Admitting that a squadron engineering officer on Guam had identified a simpler fix would invalidate 2 years of engineering effort and embarrass senior leadership. Landau completed the math anyway. Oil pressure calculations, flow rates, thermal transfer estimates, parts lists, installation procedures, total cost, less than $20 per engine. On April 5th, he requested a meeting with wing engineering staff. Denied. Focus on operational readiness. On April 8th, another B-29 burned. 9 crewmen died. Landau stood on the line and watched cylinder 14 fail exactly as predicted. Watched the fire spread through magnesium. Watched the wing fold before the aircraft cleared the field. He knew why it happened. He had 6 days before his next scheduled meeting. 6 days before another crew might burn. Across the Marianas, the 20th Air Force was losing B-29s faster than Boeing could replace them. Not to fighters, not to flak, but to engines failing at maximum gross weight in tropical heat. North Field on Guam housed the 314th Wing. Isley Field on Saipan housed the 73rd. North Field on Tinian housed the 313th. Together they launched missions delivering 10,000 tons of incendiaries each month. Every mission began the same way. Engines already at redline before wheels left the coral. Since November 1944, 47 Superfortresses had been lost to engine fires. Japanese fighters had destroyed 31. American engines were killing more airmen than the enemy. Other engineers had noticed the cylinder pattern. A maintenance officer on Tinian had filed a similar observation. The response was identical. Focus on readiness. Engine design belonged to Wright. The system was not built for field innovation. Modifications required approval from Wright Field in Ohio. Testing at McClellan Air Depot. Authorization from Air Material Command. Months of paperwork. Meanwhile, cylinder 14 would fail again. And again. Fuel injection would cost roughly $88,000 per engine. 30,000 engines in the fleet. Over $2. $6 billion in wartime dollars. 6 months minimum for Pacific retrofit. And it would not solve the cooling problem. Landau's hollow bolt modification would cost less than $20 per engine. Could be machined in any base shop. Installed during routine cylinder change. Operational in weeks. But it required someone to admit the official solution was incomplete. On April 14th, General Curtis LeMay's staff announced a maximum effort mission. 500 B-29s. Maximum bomb load. Maximum fuel. Maximum gross weight. Maximum thermal stress. Landau ran the numbers. 3 engine fires during takeoff, minimum. Possibly 5. All fatal. He had 9 days before launch. 9 days to convince someone. On April 15th, he drafted a formal technical report. 8 pages. Airflow analysis. Failure statistics by cylinder position. Temperature logs from multiple aircraft. Annotated sketches of the vortex pattern. Oil flow calculations. Installation diagrams. Cost breakdowns. Everything required for immediate field authorization. Everything except authority. And somewhere beyond the palm trees and coral runway, another crew was pre-flighting a Superfortress with cylinder 14 already halfway to destruction. He submitted the report through proper channels. Squadron engineering to group maintenance. Group maintenance to wing engineering. Wing engineering to 21st Bomber Command technical staff. Each layer added delay. Another review. Another request for clarification. On April 16th, the first formal response arrived. 17 technical questions. They challenged his airflow observations. They pointed out that cylinder number 1, the instrumented cylinder, rarely overheated. They asked why Wright Aeronautical's engineering staff had not identified the issue during 2 years of development. They suggested that field conditions on Guam might be distorting his conclusions. It was polite, professional, Dismissive. Landau rewrote the report. He explained that cylinder number 1's low failure rate proved his point. The sensor was positioned in a cooling dead zone. It measured the safest cylinder on the engine, while the actual hot cylinders carried no instrumentation at all. The data created false confidence. He attached additional temperature logs, added photographs of airflow during startup, included testimony from mechanics who had replaced the failed cylinders, documented the counterclockwise failure pattern in detail. On April 18th, another response arrived. Acknowledged receipt. Forwarded to Wright Field for expert evaluation. Estimated response time, 6 to 8 weeks. 6 to 8 weeks. The maximum effort mission was in 7 days. At current failure rates, 21 Bomber Command would lose another 15 B-29s before Wright Field even opened his file. Landau considered unauthorized testing. Take one engine. Drill the bolts. Install the modification. Run a full thermal cycle. Prove it worked. But unauthorized modification violated every regulation in the technical manual. It could mean court-martial, loss of commission, grounding the aircraft, possibly grounding the entire squadron if discovered. He could also do nothing. Follow procedure. Maintain readiness. Let the system function as designed. The safe choice. The career-preserving choice. But he kept seeing the April 8th crash. The wing folding. 9 men dead because cylinder 14 failed exactly where his analysis predicted. On April 19th, a B-29 from the 39th Group aborted a mission to Kagoshima. Cylinder 10 running hot. Feathered. Returned. No fire. No casualties. Just another sortie lost to the same pattern. Landau inspected the aircraft. Cylinder 10 was positioned exactly where his airflow model predicted overheating. The exhaust valve showed early distress. The cylinder was scheduled for replacement that night. While the maintenance crew worked, Landau measured the mounting bolts. 7/8 inch diameter. Hardened steel. Solid construction. Simple to drill. He had access to the machine shop. He had the drawings. He had the time. The maximum effort mission was in 5 days. 5 days until 500 B-29s launched at maximum gross weight. 5 days until 5,000 airmen trusted engines already near failure. At 2,300 hours, Landau walked into the machine shop. One machinist on duty. Minimal supervision. He signed out the drill press, selected the correct bits, pulled 6 mounting bolts from supply, and began drilling. Bio 300, 6 hollow bolts lay on the bench, cleanly drilled, deburred, perfectly concentric, identical externally to the originals, internally capable of routing oil directly to the exhaust valve rocker arms. 6 pieces of metal that could end the overheating pattern, or end his career. On April 20th, 4 days before the mission, he returned to the hangar. The 39th Group's B-29 sat open, cylinder 10 removed. The crew prepared to install the replacement unit. Landau waited. Day shift ended. Evening chow. Hangar quiet. 2 mechanics finishing inspections. 1 crew chief doing paperwork. Minimal witnesses. He approached the engine with the hollow bolts in his pocket. Installation was simple. Remove the solid bolts. Insert the hollow versions. Route the oil lines. Verify torque. Check clearances. Each bolt went in cleanly. Dimensionally identical. Same threads. Same torque values. Indistinguishable unless someone examined them closely enough to notice the drilled core. By 2,200 hours, all 6 bolts were installed. Oil lines connected. System complete. Unauthorized. Undocumented. Potentially life-saving. Now he needed proof. A full power ground run. Takeoff settings. 30 minutes minimum. Cylinder head temperatures monitored continuously. Oil pressure verified. That kind of test would draw attention. Ground crews would notice. Operations officers would ask questions. Someone would inspect the engine. Without the test, his theory remained theory. Wright Field would ignore it. With the test, he risked everything. Landau stood beneath the wing, looking up at the massive R-3350. He could remove the bolts, reinstall the originals, pretend none of it happened, or he could run the test. April 21st, before sunrise, before mission tempo increased, before too many eyes were watching. 1 ground run, 1 data set, 1 chance to prove that a field engineer on Guam had solved a problem that 2 years of corporate engineering had not. The alternative was paperwork and more burn wings. Landau circled the aircraft one last time. The installation was clean, precise, indistinguishable from standard hardware unless someone knew exactly what to look for. If it worked, it would expose a flaw 2 years of Wright Aeronautical engineering had missed. If it failed, it would prove squadron engineers should stay in their lane. Either way, he would have an answer. He signed the maintenance log, recorded the cylinder replacement, made no mention of the hollow bolts, and returned to his quarters. He did not sleep. He replayed airflow diagrams in his mind, rechecked oil flow calculations, confirmed pressure tolerances. At 5:30 on April 21st, he was back on the flight line. Guam was already warming. Mechanics moved between aircraft. Engines coughed to life across North Field. Landau requested a standard post-maintenance ground run. No one questioned it. The crew chief assigned a flight engineer. Landau positioned himself beside the number 2 engine, where he could see the rocker arm housing and watch for leaks or smoke. Start. The propeller spun. Fourth blade, ignition. The R-3350 settled into idle. Oil pressure steady. Temperatures nominal. Advanced to takeoff power. The throttle moved forward. 2,400 revolutions per minute. 48 inches manifold pressure. Maximum thermal stress. Cylinder head temperatures began to climb. Number 4, 370 degrees. Number 7, 385 degrees. Number 10, 360 degrees. All within limits. Landau watched for vibration, for oil mist, for any sign of catastrophic failure. 5 minutes at full power. Stable. No rising spike on cylinder 10, the usual killer. 10 minutes. Cylinder 10 holding 360 degrees, the flight engineer called. Previous runs had seen it exceed 410 degrees by this point. A 50-degree reduction. Exactly what the calculations predicted. 15 minutes. Other ground crews began glancing over. A full power run this long was unusual. The crew chief approached. Why the extended test? Validating seating on the replacement cylinder, Landau replied evenly. The crew chief nodded and walked away. 20 minutes. Cylinder 7, 378 degrees. Cylinder 13, 375 degrees. All historically problematic positions were running dramatically cooler. The hollow bolts were delivering oil directly to the exhaust valve rocker arms, cooling the stems from inside, bypassing the airflow deficiency entirely. 25 minutes. Reduce power. The throttle came back. The engine stabilized. The test was complete. Landau had proof. On April 22nd, he documented everything. Temperature charts. Comparative data from previous runs. Thermal deltas averaged 47 degrees on the critical cylinders. On April 23rd, he submitted a supplemental report. This time it included data. Measured. Verifiable. Undeniable. On April 25th, the response came. Acknowledgement of thermal improvement. Authorization for formal proof of concept evaluation. Approval to modify 3 additional aircraft under controlled conditions. For the first time, the system was listening. Landau began preparations immediately. 3 B-29 selected. Machine shop time allocated. Installation schedules coordinated. The formal evaluation was scheduled for August 10th. Comprehensive testing. Oil flow verification. Full mission simulation. If successful, the modification could be authorized fleet-wide. Then history intervened. August 9th, Nagasaki. August 15th, Japan surrendered. The war ended before the proof trial began. The test was canceled. The hollow bolt modification was filed. Documented. Archived. Never implemented. Wright Field's fuel injection conversion became the official solution. Expensive. Complex. Bureaucratically safe. Landau's field fix arrived too late. He had identified the airflow vortex. Documented the counterclockwise swirl. Proved that cylinder 1, the so-called worst-case indicator, was actually the coolest cylinder on the engine. He had drilled 6 bolts and solved the problem. But the war ended before the bureaucracy finished evaluating it. By December 1945, Landau was back in civilian life. No commendation. No recognition. No engineering bulletin acknowledging the discovery. The R-3350 continued production. It powered Lockheed Super Constellations, Douglas DC-7s, long-range patrol aircraft. Post-war improvements solved the overheating problem through brute force, fuel injection, improved baffling, larger fin area, tighter manufacturing tolerances. By the early 1950s, engines reached 3,500 hours between overhauls. reliable, stable, commercially successful. None of those fixes corrected the fundamental airflow inefficiency. They simply overwhelmed it. Landau had identified the vortex behind the propeller governor, the dead zones behind the distributors. The cylinders starved of cooling air. He had offered an elegant solution. 6 hollow bolts, $20 per engine. Instead, history chose the expensive answer, and the field engineer on Guam disappeared into the maintenance logs. But he knew that if someone had listened sooner, fewer crews would have burned on coral runways in the Pacific heat. He knew the pattern, and he had broken it. The fuel injection conversion that Landau believed addressed the wrong problem became the official answer. Every Wright R-3350 eventually received it. Carburetors replaced. Supercharger elbows redesigned. Entire fleets retrofitted at enormous expense. Billions of dollars flowed into a complex fix. 6 hollow bolts costing less than $20 per engine were never evaluated. Field solutions rarely outrank corporate contracts and Pentagon budgets. Landau's reports did not disappear. They were filed, cataloged, transferred after the war to Air Force Historical Archives, where they remain today, documentation of a flaw correctly identified and corrected too late to change history. His hollow bolt modification was never subjected to formal Wright field testing, never entered into production review, never debated in a procurement boardroom. By the time his data reached decision-makers, too much had already been invested in fuel injection. Admitting he was right would have required acknowledging that 48,000 prior engineering changes had treated symptoms rather than causes, that a worst-case temperature sensor had been placed in the one cylinder that rarely overheated, that airflow assumptions built into the engine's design were fundamentally flawed. Large organizations do not concede such oversights easily. Fuel injection worked, eventually. It forced reliability through greater capacity and tighter control. Once the engines stopped burning on takeoff, no one cared which underlying flaw had mattered most. The elegant answer was buried beneath the expensive one. Daryl Landau left the service at the end of 1945 and returned to civilian engineering. He did not campaign for recognition. He did not challenge official narratives. He carried the knowledge quietly. Decades later, his discovery appeared briefly in a book about B-29 development, a few paragraphs, almost an aside, in the shadow of atomic bombs and strategic bombing doctrine. But those paragraphs matter. They record that someone on a coral runway in Guam saw what others missed. That observation and data outpaced bureaucracy. That a field officer with graph paper identified a vortex that engineers in climate-controlled offices had overlooked. The crews who died in April, May, June, and July of 1945 did not perish because the problem was unsolvable. They died because the solution moved too slowly through the system designed to approve it. Because regulations value process over improvisation. Because established programs defend themselves. Because simple fixes threaten complex investments. History remembers the atomic bomb. It remembers Curtis LeMay. It remembers the B-29 as the bomber that ended the war. It does not remember the counterclockwise swirl of air around a propeller governor, or 6 hollow bolts drilled at 0300 in a machine shop on Guam. But those details mattered. They were the difference between 410 degrees and 360, between valve failure and safe climb out, between fire and survival. Landau knew that, and now you do.